Welcome back to differential equations. In this video, we're going to be looking at polynomial approximations for solutions to initial value problems. You can see behind me already, I have the definition of a Maclaurin polynomial written down. I'll get my head out of the way in just a moment so you can get the rest of it if you don't remember it offhand. But the idea here, if we know the value of the function and the first several of its derivatives at the point 0, we have enough information to approximate the value of the function in general. And so if I get my head out of the way, we can look at a specific initial value problem. So for example, if I have the differential equation y double prime is equal to x plus y minus y squared, along with the initial conditions, y of 0 equals -1, y prime of 0 equals +1. This is a differential equation which we do not have the tools to solve right now. It is non-linear. It has a y squared, a non-linear term. So that's a problem. And it is second order. If we had a first order nonlinear differential equation, we might be able to manage. But with a second order equation, things have gotten a little bit too complicated to manage. And so one tool that we can use is the Maclaurin polynomial. Let's assume that this initial value problem has a polynomial solution. And the higher the order we decide to go for, the better our approximation is going to be. Of course, the higher the polynomial we go for, the more tedious the calculation is going to be. So we need to find a fourth degree polynomial approximation. Right? That seems like a good balance between we have some detail and we can actually achieve this in a reasonable time frame. Some things that I want to mention here. In order to be able to find a fourth degree polynomial approximation, first of all, we need to have an initial value problem. And as long as the initial point is 0, I'm working with x equals 0. You could do the same thing with t equals 0. But as long as that initial point is 0, you're in good shape. If it was non-zero, then instead of a Maclaurin polynomial, we could have used a Taylor polynomial centered at whatever that point happens to be. But initial value problems where the initial point is non-zero are relatively rare, so I'm not going to worry too much about it. The other thing that we absolutely need in our differential equation is that we have to be able to solve the differential equation for the highest order derivative which appears. If you cannot do that, the process will not work. Whenever you have a linear differential equation, that's something that you're guaranteed to be able to do. If you have a nonlinear equation, sometimes you can, sometimes you can't. Right? But we're going to rely on the fact that this equation is actually given in that form. In general, we need an equation that can be written in that form. Because what we need to find are y of 0, y prime of 0, y double prime of 0, y triple prime of 0, and the fourth derivative of y at 0. Right? Those are the parameters that we need in order to write the fourth degree polynomial approximation, right? Just going up until n is equal to 4. The first two are given to us. y of 0 is -1, y prime of 0 is 1. Those are the initial conditions. The next value that we need, we can actually get right from the differential equation. Right, so there's 1, there's 2. For 3, we need y double prime of 0. Just take that equation and plug in 0 for x. This is going to be 0 plus y of 0 minus y of 0 squared. Well, 0 is 0. Y of 0 is -1. Y of 0 is still -1. You square that, you get +1. So it's -1 minus 1, which is -2. Right, there's one more value on our list. Next, we need y triple prime. And that's where we have to start getting creative. Although the trick that we use here is not that difficult to follow. By definition, y triple prime is the derivative of y double prime. And of course, y double prime, we know from our original differential equation. This is why we have to have the original differential equation solved for the highest order derivative that appears. So we want to take the derivative of x plus y minus y squared with respect to x. So again, be careful here following the chain rule. The derivative of x is 1. The derivative of y is a function of x. So when we're differentiating y with respect to x, we get y prime. The derivative of y squared is 2 times y, but then using the chain rule, multiply that by the derivative of y prime. There is our expression for y triple prime. Evaluate this, add 0, we get 1 plus y prime of 0 minus 2 times y of 0 times y prime of 0. It's almost going to scroll off the screen, so let me scroll up for just a moment here, grab all of my values that I've gotten so far, and make sure that they come along with me because I am going to want to be able to reference those as I complete this problem. Y prime of 0 is 1, y of 0 is -1, y prime of 0 is still +1, and I get that the third derivative is 4. All right, let's keep sliding this down with us. We still want to be able to work with it. I can move the screen just a little bit here because we have one more to do. I need the fourth derivative of y, which is of course the derivative of the third derivative. And the third derivative is right there. 1 plus y prime minus 2y prime. All right. And taking care here, the derivative of a constant is 0. The derivative of y prime is y double prime. Then I have a product. The derivative of 2y is 2y prime times y prime, and then 2y prime times the derivative of y prime, which is y double prime. Right, so the fourth derivative of my function here is y double prime minus 2 times y prime squared minus 2 y prime y double prime. And again, I have to just keep grabbing this and pulling it along. I wish that I had a nice way to make that float so that we could just keep looking at it. But unfortunately, my computer's not quite powerful enough to pull that off. That's an upgrade I need in the future. But my goal here is to write not y to the fourth as a function, but take y to the fourth and evaluate it at 0. So I'm going to get y double prime of 0 minus 2 times y prime of 0 squared minus 2 times y prime of 0 times y double prime of 0. I barely have enough room to put that all on the screen, but that's okay. I do have enough room, and that's all that matters. Y double prime of 0 is negative 2. Y prime of 0 is 1. So I've got negative 2 minus 2 plus 4, which I guess comes out to be 0. That's convenient. Pulling my list along with me one last time, I can now write that y of x is approximately equal to y of 0, which is negative 1, over 0 factorial, plus y prime of 0, which is 1 over 1 factorial times x, plus negative 2 over 2 factorial times x squared, plus 4 over 3 factorial x cubed, plus 0 over 4 factorial x to the fourth. And I might as well just clean up all of those fractions. I get negative 1 plus x minus x squared plus 2/3 x cubed. All right. And that's really all there is. It's just a matter of taking the time and being careful with this, and things should work out. So I would like you to try this initial value problem. I have y double prime is equal to x squared times y, along with the initial conditions y of 0 is 1 and y prime of 0 is 0. In this particular case, a polynomial approximation is probably not the best tool for the job, but that's what makes it a great example problem here. It is relatively easy for polynomial approximation, which makes it a good first example here, even though you could probably solve it exactly using other tools instead. And I would like you, as I did, to find a fourth degree Maclaurin polynomial approximation for the solution to this differential equation. All right, take a couple of minutes, see what you can do with that, and I'll see you in the next video.